So one of our more intellectual mathematicians years ago, Euler, E-U-L-E-R, pronounced Euler, just like this. He decided to do some work with this expression right here, 1 plus 1 over n to the power of n. And he discovered that as you take 1 plus 1 over n to the power of n to infinity, that the number gets bigger and bigger and bigger, but only a little bit bigger and bigger and bigger. If you look at the graphing calculator here, I entered 1 plus 1 over x to the power of x. And what I want to show you is what happens when we look at the graph. So the graph of this on the right-hand side from when x is 0 going to infinity, you can see that the graph is increasing, but it looks like it levels off. If we look at the table generated when I increase my power here, so I'm looking at this expression right here, 1 plus 1 over n to the n. As n gets bigger, watch what happens to the value of the expression. When x is 0, we have 1 over 0, that's undefined. Can't do that. When x is 1, you get 2. When x is 2, you get 2.25. When x is 3, 2.37. The number keeps getting bigger and bigger. However, it is not growing exponentially. Through the roof graphs like we did yesterday. And as we increase this value of x, look at the values in the table. We started at 2, we were at 2.5, 2.6, 2.64, 5, 5, 5, 6, 6, 6, 6, 7. And you can see that the number is getting bigger, but as we increase x, it gets bigger slower. And every number is getting bigger. But it's getting bigger way slower. And we're only in the 60s right here, 70s. 2.70, 2.700. And if you keep going, 2.703s, 2.704s. And it keeps going at a smaller and smaller rate. So it's flattening out, which means we say that this function has a limit. What Euler decided to do was say, look, as n goes to infinity, in other words, you have 1 plus 1 over 10,000, raised to the 10,000th power, we're going to approach 2.71828, this irrational number. And that irrational number we're going to represent by this lowercase e, and we're going to call it Euler's number. So on your calculator, you should be able to take e raised to the power of 1, and you should be able to get this number. Some of you who have an e button on the calculator, you should be able to get e, and then press the enter button, and you should get Euler's number. You want to make sure you can do that right now. So for example, for me, I can do the e button and hit enter, and it'll give me that number. Or I can do e to the power and put a power of 1 and get the same value. E to the first and e obviously are the same. Is there anybody who can't get this number to appear on your calculator? Ways to handle this. These expressions here, the first expressions we're going to look at are no calculator. Simplify the expression. E to the 9th times e to the 6th. When you simplify that expression, e to the 15th. The end. You circle it. I don't want an approximate value. I want a simplified value. Simplify means do what? Yeah, what does simplify mean?
Go to the end of the
Get rid of parentheses, combine like terms. two things. Get rid of parentheses, combine like terms. We got rid of parentheses. We're done. There are no like terms, only one term. See if you can do B and C on this. See if you can simplify B and C. Look at the top ones first. The first one is example B. For example B, Natalie, what'd you get? 5 e to the 5th power.
That's correct.
60 over 12 is 5. 8 minus 3 is 5 on the power. 5e to the 5th. The second one is a little trickier, and there's also temptation to do something wrong. Johan, what'd you get on this one?
It's
Negative 1,000. Negative 15x, and of course you change that to negative 1,000. Well, let's just do the negative 1,000 over. There you go. The only problem with your first answer was the negative in the power, right? So let's just drop that out of there. Move it down. The negative 1,000 stays where it is. Is it negative? Then we're good. There's nothing wrong with negative or with powers. Powers, we like powers. We don't like radicals. We don't like fractional powers. And we don't like negative powers.
We don't like parentheses.
When we're simplifying, you typically do not. Take a look at these two examples. This time you're using your calculator. So if we did e to the 6th, that's not e to the 6th, we want e to the 6th. You should get 403.429. You didn't get it?
Wait, what would you, if you have to round it?
Yeah, that would be good.
What did you get when you rounded it?
403.429.
I mean, when you round it.
That is rounded.
You said it to go to the 3rd place.
I did 403.429.
Like if you looked right.
What did you, let me change the question. What did you get when you rounded?
I just got 4.43.
I need a bigger voice.
0.43 at the end.
Okay, if you went one more decimal place, that would have been 3 decimal places, right? You went 2 decimal places.
No, I rounded. 2, if you look to the right, it's higher, so you add it.
Here's what I mean when I say round to 3 decimal places. 403.429. This is the 3rd place, right?
Yeah.
That's how many places are in the answer.
So you don't have to round that?
You do have to round that, but I want you to round to the 3rd decimal place. So I want you to look on your calculator, and I want you to look there, and what's in the 3rd place? You can look up here.
Can't see it from there.
Oh. This is 4287935. The 3rd number in the decimal places is an 8. To the right of the 8 is a 7.
So then you round it.
And you would get,
9.
which is what I got.
Okay.
But we need to go 3 places. Everybody good with the first one? The second question is e to the negative 0.28. Be careful that you don't use a minus there, that you're using a negative. And again, this is all dependent upon your calculator. E to the negative 0.28. And we're going to round to the 3rd decimal place. Looking 1 to the right of there is going to give you 0.756. 0.756. Everybody good on those two?
Are you always going to want to round to the 3rd, unless you say Otherwise,
Your answer,
You
you're
always round to how many places? 3, unless it's
dinero.
money.
uh,
You might have heard that earlier.
right.
It's like 1,000 times.
A dozen times. Said the one around is the 2 places. Yeah, seriously. So what did this come out to be? 756. 0.756. All right. Now, the book, for whatever reason, I'm not really clear on the reason, is treating this like it's 2 separate parent graphs, and I don't want to do that. I want to treat e to the x as the parent graph. Right? E to the x is the parent graph. So, with a parent graph, there is not a lot of mystery here. We have a horizontal asymptote for 0, 0. If we're going to graph this, it's an exponential function. How do you know?
It's to a variable.
It's raised to a power that has a variable in it. Every exponential function graphs the same way. Write 1 up. Every exponential function, y equals b to the x. So every one of these functions is right 1 up b, right 0 up 1, and left 1 up 1 over b. You need to have those diagonals. We need to know those backwards and forwards. So when we're going to graph this function, we're going to go right 1 up e, which is 7 is enough. A little bit less than 3. Right 1 up 2.7, which is right 1 up e. If you make your point fat enough, you're definitely going to hit it. Right 0 up 1. And left 1, say it without simplifying. Left 1 up 1 over e. What is e almost equal?
1/3.
Almost 3. So we could go left 1 up about 1/3. And you can obviously do 1 divided by e, or 1 divided by 2.7. You could get a more accurate estimate. I don't know that it needs to be more accurate. We're just doing it as a graph. If your graph looks like that, we're good. Once I can see those 3 points, we're good. Right 1 up b. Right 0 up 1, left 1 up 1 over b. Take your calculator out and divide. 1 divided by e. If you can't remember what that value is going to be. Anybody have a question on this? This is a parent graph. It shouldn't be any different than what we did yesterday. The only change is that we have a variable base, but that variable stands for 2.718. We should be good to go. This slide is from chapter 2. So from our notes in chapter 2, it has been on the board multiple times. I would say 5, 6, 7 times throughout the course of this class. We learned about A is the vertical stretch factor. We learned that the opposite of whatever's with x is called c, and whatever's after the function d, and that becomes your translation vector. What we haven't really learned about is b, because we haven't had a single b in the whole course. We should have, but the curriculum doesn't have any in the book. It's really kind of silly and a little bit disconcerting from my perspective. Whatever number you're multiplying x by in the function, in any function, if you take the reciprocal of that number, that's what this is telling you, 1 over b, you have the horizontal stretch factor for the function. The horizontal stretch factor impacts the lefts and the rights, just like the vertical stretch factor impacts the ups or the downs. So when you multiply the ups of your parent graph by the VSF, we do the same thing. We take 1 over b and we multiply the lefts and the rights. in your parent graph. So no difference except that you're dealing with the horizontal component. And you're either going to make it bigger or smaller depending upon what the reciprocal of b is.
Are we talking about the same b that's in y equals b to the x?
No, that's little b. This is big B.
Oh.
F of x is the function. What are you multiplying x by? That's big. Look at this right here.
Yeah.
This is big B.
Okay.
Right? So the first one that we're going to look at is y equals e to the negative x. And when you make your list now, because this is not a parent graph, we need to make the list. We need to include in our list the horizontal stretch factor. Now the only thing this graph has is a horizontal stretch factor. Everything else, more or less, remains the same. The parent graph is y equals e to the x. Translation vector 0, 0. Vertical stretch factor is 1. We're not doing anything there. Horizontal stretch, or horizontal asymptote, is still y equals 0. But you can see that x is being multiplied by a negative 1. So the reciprocal of negative 1 is negative 1. So that is your horizontal stretch factor. You'll see shortly that we'll put different things in there like a 2 or a 1/2, and that you take the reciprocal to get the horizontal stretch factor and it changes what b is. When we graph, there's not a lot of change here. We're still graphing the same horizontal asymptote. We're still, you better shut that off. We're still starting at the origin. We still go right 1 up e, but when we have a horizontal stretch factor of negative 1, right 1 becomes left 1. So left 1 up e. Right 0 up 1 becomes right 0 up 1. Left right 0 has no impact from a horizontal stretch factor. Wait, what? We're going to multiply what comes after the word left or right by the horizontal stretch factor. Right 0. What do we multiply it by? What were you thinking?
I was just looking at it as something right.
Okay. Yeah, so we gotta think left, right. So right 0 up 1 is gonna stay right 0 up 1. Or somebody said, oh, it becomes left 0 up 1.
Yeah.
Okay. It became left 0 up 1. Whatever. Left 1 in the parent graph, what do we normally go up in the parent graph? 1 over e. Left 1 is going to become right 1 up 1 over e. And 1 over e is about 1/3. So our graph is going to come down and technically become a decay graph. Horizontal stretch factor negative flips you horizontally. So our parent graph, here's our parent graph with a negative horizontal stretch factor. All we ended up doing is flipping horizontally, and we got this graph. That's what the negative horizontal stretch factor did for us.
Is that the same as averaging this function y equals 1 over e to the x?
1 over e to the x is the same as e to the negative x, yes. Change this back. So this is y equals e to the negative x power. Remember, 1 over b, not b, is the horizontal stretch factor. And you're going to multiply the left rights by 1 over b. Whatever comes after the word left or right, you're going to multiply it by 1 over b. That's your horizontal stretch factor. And it only impacts the lefts and the rights. This 3 is not a horizontal stretch factor. It's a vertical stretch factor. If it was horizontal, it'd have to be up here. And it'd have to be to the 3x power. You're going to be standing in a minute. E to the x is still our parent graph. The only thing we have here is a vertical stretch factor. So when you make this list, it's still y equals e to the x. Translation vector is still 0, 0. Vertical stretch factor, 3. No horizontal stretch factor. And the asymptote is still at y equals 0. The only thing we're doing here is stretching our parent graph taller. So we start at the origin. Right 1 up E becomes right 1 up. You're way ahead of where I need you to be. Right 1 up E becomes right 1 up 3E. If you don't know what 3E is, which I don't, you need to find out. So on your calculator, you multiply 3 times E to figure out what that value is. It shouldn't be a big number.
That's like some.
Which means your point needs to be above the 8. You need to be specific. If the point is up here, I'm going to mark you down because it's not in the right spot. It needs to be about 8.1. Right 0 up in the parent graph, 1 becomes right 0 up 3. And left 1 up 1 over E becomes left 1 up 3 over E. Again, you're going to need to use your calculator to find out that 3 divided by E is 1.1. So our graph is going to push the asymptote out here and start coming off, hitting, going up. So very important that you have the points in the right locations. Well, you would have something, you would have 3 times, in a set of parentheses, 3 times another set of parentheses, x plus 4, close, raised to the power of 2. So it would look like y equals 3 times, usually we put a bracket here, 4 times x minus 1 squared plus 8. So your vertex is at 1, 8, vertical stretch factor of 3, horizontal stretch factor of 1, 4. Okay? But the book totally ignores this. In the parent graph, we go right 1 up. In the parent graph, we go right 1 up. In the parent graph, we go right 1 up E. That's right here. We have a vertical stretch factor of 3, so we're going to go right 1 up 3E. What's 3E equal? That's for your calculator to figure out. And same thing on the left, 1 up 1 over E becomes up 3 over E. But you have to find those decimals on a calculator, unless you want to memorize them. Not the way to go. Somebody else had a question? Good? Okay? So again, see if you can do this one by yourself, and I'm going to tell you right now to be careful with that -2. Okay, so what's the parent graph? Still 0, 0, right? Yeah. Vertical stretch factor is still, and then the horizontal, careful, -1 over 2. Horizontal asymptote y equals 0. Look, this is hard because we haven't done much of it. B is what you're multiplying x by. 1 over b is the reciprocal of that. That's your horizontal stretch factor. So we have to have a negative 1/2.
Oh, no, sorry.
Okay? When we graph this, we're going to go right 1 up e. Right 1 up e is the parent graph. What do we do? Left to half, still up e. Right 0 up 1. What do we do? Right 0 up 1. It has the horizontal stretch factor has no impact on right 0 up 1. Only vertical stretch factors. Is B is negative 2, right? What is the horizontal stretch factor? Again, this is what I just did. I went right back here, and we said B is what we multiply x by, and that was negative 2, right? In your notes, it says 1 over B is the horizontal stretch factor. So in this problem, B is negative 2. The horizontal stretch factor is 1 over negative 2. Oh, absolutely. It doesn't say the negative of it, it says flip. Okay? Normally in the parent graph, we go left 1, up 1 over e. What are we going to do in this one?
Right 1.
Right 1/2 up e. Or 1 over e, thank you. Whoops. So we're up a little bit, but you get the idea. Okay, so now we're going to throw both a vertical and a horizontal stretch at you. When we make our list, there's not a lot of deviation here. When you make the list, y is equal to e to the x. That's our parent graph. It seems to be the theme today. The translation vector is still 0, 0 on this one. And the vertical stretch factor on this graph is 4. The horizontal stretch factor, be careful, is 2. And the horizontal asymptote is still y equals 0. Is everybody seeing the horizontal stretch factor being 2? Remember, can you tell me what b is in the picture, in the equation? How do we find out what the HSF is? 1 over b. Use your calculator if you can't do it in your head. 1 divided by 0.5 is 2.
Yeah.
And for a lot of us, that's really a good way to go. Just do it on the calculator. Get that decimal. Sometimes it's a decimal, sometimes it's an integer like this one. But it's always 1 over whatever you're multiplying x by. Okay? Or you could turn this into a fraction. The 0.5 as a fraction would be a half. And then take the reciprocal. When we graph this, the parent graph says right 1 up e. Based on our list, what do we do? Right 2 with, what was it? 4e. Right 2 up 4e. I don't know what 4e is. Sounds like an apartment. What is it? 10, almost 11. So right 2 up almost 11. So we're way up here on my graph. In the parent graph, we go right 0 up 1. What are we going to do? What about the left, right? So it's still 0. It's right 0 up 4. The left rights don't get impacted when it's left right 0. And then we go left 1 up 1 over e. What are we going to do?
2.
Left 2,
Up.
up
4 over E.
4 over E. Now what's 4 over E? I don't know. 4 divided by E is 0.74.
1.47.
That sounds better. 1 point what?
47.
Going too far. Left 2 up 1.47-ish. So we're going to get asymptotic out here. You're going to have a graph that looks something like that. It looks like I missed it a little bit. So I have just drop her down a little. It's pretty close. Any questions on that one? So here you can see we have stretching and translating going on. The translating shouldn't affect us. And if you understood just plain stretching, once you translate that origin, that's the end of the stretch deal. See if you can make your list first before you start doing your graph. And let's talk about the list. So in the list, parent graph, we're still y equals e to the x. But this time we have a translation vector. What is it? -2, -4. There's a couple people who are still changing the -4 to a positive. Be real careful. The D value doesn't have an opposite side. Only the C value. Vertical stretch factor.
1.
Horizontal.
I put -0.6.
Okay. How about as a fraction?
-1/3.
-2/3. And then the horizontal asymptote is going to be y equals -4. So y equals -4 is always the D component of your translation vector. So -2, -4, if I make a little, just make a little translated origin right there. It's not part of my graph. It's just my starting point. Now, I do what we've been doing in the last 3 graphs. How do we get the -2/3? Well, there's a lot of ways. -1.5 is equal to B. So 1 over -1.5 is the horizontal stretch factor. You don't want to have a decimal in a fraction. You can multiply top and bottom by 10. So you get 10 over -15 or -2/3. You might know that -1.5 is equal to 3 over 2. So the reciprocal of -3 over 2 is -2 over 3. But if worst comes to worst, you do it on your calculator and you do 1 divided by -1.5 and you round. Because it's really not critical to have the exact value here, just that you have the value. Because we're graphing.
It would be -0.6.
-0.6 repeating.
Yes.
So it's anything in that ballpark would be great. So if we're going to graph this, from the origin, we normally go right 1 up E. Right 1 up E. What are we going to do here?
Right.
Left 2/3, still up E. So right 1 up E would be right here. We're going to move that to left 2/3, but it's going to stay up E. We're not really doing anything except switching the horizontal component. Normally in the parent graph, it's right 0 up 1. Do we leave that or do we have to move it? We leave it. And in the parent graph, we normally go left 1 up 1 over E. What are we going to do?
Right.
Right 2/3, and it stays up 1. So we're flipping everything horizontally, and when we bring this graph down, whoops, got a little bit more than I want there, but that's the idea. Remember we talked about Euler's number at the beginning, this mathematician? Well, Euler did a lot of work with limits of this sequence, 1 plus 1 over n to the n power. If you take his formula and plug it into our compound interest formula, the limit of 1 plus 1 over n to the n, what did we say that was going to equal? E. So this formula, which we don't need for our purposes, becomes this formula for compound interest, where you're compounding what we say continuously. You know, we can compound monthly, daily, hourly, minutely, secondly, nanosecondly, and smaller and smaller and smaller. And if we get to the point where we're compounding continuously, we make the compounding period infinitely small, and we therefore have an infinitely large number of that the power is raised to. We get this formula. That formula is what I call the shampoo formula. Now, I'm willing to go a long way to connect dots in this class. So I've left it here all semester waiting to connect the dot, right? And here we are connecting our shampoo formula with the bottle that's been sitting here all semester.
Oh, I've been so curious.
It's not just a shampoo, you know. It's a conditioner and a shampoo all in one. You don't have to do two things. You're saving water, the environment. Oh, this is fantastic. You too can go and get Purge. It's at the stores right now. This is medium conditioning formula. But I think they probably have like, what would the other choices be? Anyway, per our shampoo formula, when can we use it? We can only use this formula when you see this word, compounded continuously. So if the word continuously is not with compounding, you can't use the shampoo formula. It's not going to stop some people. They're going to use it anyway because it's a fun formula. But you can only use it when the compounding is done continuously. P is still your starting amount, called principal with an investment. E is Euler's number. R is your interest rate. Don't forget the interest rate must be as a decimal. And T is time in years. Don't forget it has to be years. So if you were given something like 9 months, you've got to change that to years to 3/4 of a year. So T is time in years. R is a decimal for the interest rate. P is your starting amount. This is all done with write the plug-in and then use your calculator. So when we look at this example here, we have a $3,000 deposit, 3.5% interest for 3 years. So we're doing the shampoo formula, and we're doing that because it has the word continuously in the problem. So we know we're supposed to use the shampoo formula. You've got to be very careful with this when you plug it in. A equals 3,000 times E raised to the 0.035 and 3 years times 3. That's all you have to have on your paper, and then you would say A is equal to, and you should be able to come up with your calculator how much money you would have in the account. So take a second and so what did you get for a value of this investment in 3 years?
3,332.100 and
Wow, really good. 3,000.
132.
You need to round to 2 decimal places. All right, $332.13. Now, I've said this before. I used to have a sign in class that said there was no stupid questions. Sometimes there are stupid questions. There's also stupid answers. And I get, you can't imagine, well, let's see. I've gotten answers like, for a problem like this, I'll get $228,958.18. I want that person to take care of my money. $200,000, 3% interest in 3 years. You started with $3,000, now you have over $200,000. That does not make sense. I've had people tell me that we have $1,215.84 at the end of 3 years. That doesn't make sense. You have started with $3,000. This is not decreasing in amount. You're earning interest. So what we do is, if you want to know if you're in the ballpark, use the rule of 72. And I show this to all my classes because it just makes good sense to say, does my answer make sense? The rule of 72 is just an approximation. Hey, the rule of 72 is an approximation. 72 divided by whatever your interest rate is will tell you how long it takes to double your money. So if you have 72 and you were getting 10% interest, 72 divided by 10, don't change the interest to a decimal. 72 divided by 10 is how much? 7.2. It's going to take you a little bit more than 7 years to double your money. If you had 3.5% interest, like the problem we're working on, 72 divided by 3.5 is 20.57. That means over 20 years to double your money. If you have an answer of more than $6,000, which is double the $3,000 original, in 3 years' time, something is wrong. 3 out of the 20 years, you shouldn't have anywhere near double $3,000, and we don't. Does that make sense to everybody? Let's see who's been really paying attention in the last few days. What does the graph look like for this function? No. Wrong answer. I may look like that, but not the right answer. Nope. 2 words. What does the graph look like for this function? No, there's a you can graph this. So my 2 words are, who cares? Who cares? I don't want you to have to graph this. If you want to figure out what this is, we don't want to do it graphically because this is an application. This is your assignment.